Excuse the, I might be clearing my throat a bit and like, coughing here and there. I got COVID, so, but we're all getting dandy on that. And I'm recovering. So, it's January 5th. Oh my God, is it January 5th? Yeah, it's January 5th, 2022. Happy New Year's, everyone. Let's get started with the new updates for the project. So, number one, little TLDR, we are still testing out the STM 32F1 CAN bus driver. That's been a thing. Um, yeah, it's been a lot harder than we expected, but we're seeing a way to completion. So we're almost there. Just got to get some stuff done with the timing. Um, I said before it was STM-F4. I was actually incorrect. It was actually the STM-F1, but getting that to work on the STM-F4 is extremely easy. It should just be changing the register addresses over. A couple items we're going to talk about today is reusing GitHub action workflows, which is going to be really useful. Updating the timer interface, which I was working on the system timer today, and I realized that there were better ways to do things. And then finally, we're going to go into Leaf, which is the big item for today, which I'm really excited to talk about. So let's jump right in. Reusable GitHub action workflows. So if you didn't know what GitHub actions are continuous integration built into GitHub. If you don't know what continuous integration means, it is where, so the idea is like continuous, so integration, getting something to integrate into something else, continuous, having all the time. It's meant to be a way such that, let's say, you update your code base. You want to ensure that the libraries, or like that your code that you put in did not break anything else. At Google, we call them pre-submit checks. There's probably other words for it at other companies. So anytime we go and push code in, we want to make sure that it fits our style. We want to make sure that the naming convention has been adhered to. We want to make sure that that the documentation is there. We want to make sure that the spell checking is the spelling is checked, and we also want to make sure that the test code. Probably the most important thing is that that whatever code you put in does not break other code. That's paramount, because if you start putting in changes, it starts breaking other things. That's a problem. So, one of the most annoying things about GitHub Actions for years since it's been out is the fact that you couldn't reuse them. So if you made a good action for one file or for one place, you could either put it on the marketplace or build it such that it can be called like its own module. But there are a lot of weirdness that kind of comes with that, and it's not as useful. What people really want to do is say, hey, I have a lot of repos, and I have like one where it's like kind of the main one that has like the main jobs I want to run. Can I just pull that in? Can I just reference them from afar? And for years, people have been asking for that, including myself. And eventually, we got that. We got that like recently. So what I've actually done is libembeddedhal has the main lint, doc, and test workflows. A little asterisk there. I'll talk about that in a sec. And they've been made remote callable, meaning that you can add linting, docs, and eventually in the future unit testing to your project as simple as this. So here's a bit of a link. So let this redirect us. So for Cortex, you can see that for all the jobs it has, it just needs to say, hey, libembeddedhal, GitHub workflows, lint, YAML. I want to go from main. I want the main version of this. And I think it makes sense for our pre-submit for this thing's main to always point to the main there. Using a older commit or like that seems like you are trying to opt away from keeping your code up to standard. Same thing with docs. So basically, if you want to use all of the stuff that we use to generate documentation, it's all there. To show you what the real ones look like, did I put a link there for the real ones? Yes. So if you want to see libembeddedhal's workflows, you can find here. So we can take a little look at, I'm going to look at lint. So we have a couple of jobs here. We know that it runs on Ubuntu 20. It checks out all the code first. Installs Clang format. Install cspell, which is used to spell, check spelling. Install Clang 11 dev. Just want to make sure I didn't log off. Okay, I'm still connected. Cool. Because FYI, I've had many times when Discord logs me off, but it happens only when I'm in Sacramento with my mom's internet. So, beside the point. Install Clang dev, install the Clang and PyYAML pip libraries. This one's a bit interesting. I'll talk about that in a sec. But basically, we run the name convention check, and then yes, we run the name convention check. Then we run Clang format here, and then we run the spell check. So cspell, find everything that's basically a header file, run it through here. Although I need to change this. Yeah, I think I need to change this to use the same format that we're using for Clang format, because I think this is limited, very, very limited actually. The interesting thing here that I wanted to bring up is that with workflows, you're allowed to give them inputs. So basically, we're able to tell them like, hey, if I go over back to libarm cortex, when you call it, you have to specify this variable library libarm cortex. Now, at the moment, we're not using it. I thought that maybe being able to use that name would be useful. For example, if you go like to the main root here, include / then it has like the name. So I think I might have to use it that way, but I discovered a clever way to get around that. So we don't really need it, but it's there. But the interesting thing here is that because I required this, it must always be filled with something. Therefore, if it's ever empty, it means that you're actually running on libembeddedhal. Like you were pushed from here. That's all to say is that like what this actually does, this little line of cloning the naming, and then also this little line of cloning the Clang format. This is a way to force anyone who uses our particular workflows to also use our format style as well as our naming style. This is not like a bad thing per se. This is actually a way to keep all of them consistent so that you don't have to actually copy the naming style file. You also don't have to copy the Clang format file either. Hold on a sec. Mouth's getting a bit dry. Okay. So so this ensures that we always clone from the main repo of libembeddedhal. So we're keeping up to date with our formatting and with our naming style. So one day libarm cortex may just flare up and say, hey, we failed. And that means that we need to go in there and fix it up. Okay. And that's pretty much it, though. You can look at the other workflows if you're interested, like how docs is generated. One thing to know is that like not only do we generate documentation, but the documentation flow can also error out by basically telling you that you did not complete. If you have anything in your code that is not documented, that gets considered an error. So and we use that in order to say, hey, document all your code. So you're actually forced to document all your code as well. At least the public APIs need to be documented. So that is pretty much reusable workflows. Just gonna go through a couple things here. It's pretty minimal to add in this capability. You just have to simply add in the on workflow. We're reserving the required input library name for future usage. Clang format check is fixed, and I had to fix an issue with Clang format, so in that little change I had to fix that as well. We basically force you to use our naming style, naming convention, or style guide or style format, and also our naming. Although cspell, you have to define that yourself because there might be names in your platform or your driver that don't make sense in libembeddedhal. For example, systick for like system tick timer for ARM Cortex. That's not going to be in libembeddedhal because it can be used for any platform. So that needs to be on its own cspell file. Just basically has a whole list of words to ignore. And I'm still not sure if there is a reasonable way to make test and doc more automated. By that I mean doc. I would desire doc not needing for you to copy files in order to make that thing work, but I think that's just how it's going to be. And test, I don't think I'm going to have to get around that either. So that's just that. Yeah, and if you have any comments or questions, bring them up now, or you can just interrupt me while I'm talking if there's anything that you just don't understand. Okay. So yeah.
Was this part of the? You said it's not part of the marketplace. It's something else.
Yeah. So you have the GitHub Actions, which you can put on the marketplace, on the Actions marketplace, but they act differently than just a normal job would. They're kind of, it's like a weird type of sandbox they're put into in order to do their work. This is more just simply taking a a actions YAML file from somewhere else and just linking it to yours and saying do this work. Basically, take everything that's inside of here and do it right here.
Okay, so you just have to point the workflow to your repo and it'll run it for you somewhere else.
Yep. In this case, the organization is called SHACdev2, libembeddedhal is the repo. Now we go into the folder names. From root, it's GitHub workflows lint, and then you just specify what commit you want to use or tag you want to use.
Okay, so what is this called again? I've never heard of this.
So this is called GitHub. This is called GitHub Actions. If I go down to actions over here, you can actually see a couple actions that have been running. But if you're talking about like the reusable thing, that's actually new. So look up reusable workflows.
Okay. Yeah, that's what. Okay, I'll look that up. Awesome.
Yeah, reusable workflows. Yeah, like I think the one person who reminded me that was even a thing to look into was Harmander, who straight up said like, "Hey, I saw your name on one of these online," and I was like, "What?" And then he saw my comment saying, "I really want this feature," and I was like, "Oh right," and he's like, "Yeah, they have it." I'm like, "What? That's crazy." So we implemented it, and it's made my life. Once I got everything all kind of squared away, I think it's gonna make adding other libraries to stuff a lot easier. The one reason why test has an asterisk next to it. Checking the time. The reason why test has an asterisk next to it is because libembeddedhal and a lot of the libraries aren't on the Conan store, and the way that we do tests, basically, like in order to fetch those libraries, that stuff needs to be on the Conan store or the Conan repository or index. So until we have those on the index, testing won't actually work. So that's something I'll be working on hopefully soon, but I'm still have this little feeling of like that there's more I need to do before I put the stuff out there on the index. Or I get to do it now and just make a whole bunch of different versions and just kind of go crazy with it. Any other questions? Cool. So here's another little thing. Updates to the timer interface. Move this up a little bit. So this is what we had before. We have like this class timer, driver, we have controls, type, and a couple other stuff like here. Is running, control, attach, interrupt. Here we just have is running, clear, and schedule. Well, actually the same number of functions. But you'll notice that there's some things that are missing. For example, controls and type are gone, as well as the control function and this type parameter here. Basically, so this timer here looks a lot like the counter class that we have. We have a counter class. So if you have a hardware counter that just counts up and up and up, or down and down and down, however you want to do it, or they're actually supposed to go just up, but like it doesn't really matter, honestly. It's a counter, just counts for you. They don't have the same exact interface, but they're supposed to have different semantics. The way that they operate is supposed to be different. I guess the one key difference would be that this one has an attach interrupt. I looked around, I thought about this one. I was starting to implement this for SysTick, for ARM Cortex, and I realized it just didn't make a lot of sense. Like this control thing, why are we starting, stopping, and resetting the timer? Like, you can do that with a normal timer, but normally when you restart it, you start back from where you were before. You know, like it just didn't seem. It was getting a little complicated for what I was doing to make all this stuff work. And then I looked at all these other implementations for timers, mostly from like JavaScript, from Java, from SysTick itself. And I thought to myself, you know what? This is all we really need. A way to check if it's already running. A way to schedule a callback and a delay. So from now, I want to run this callback 500 milliseconds in the future. And let's say at some point we realize, hey, we don't want to run that thing anymore. Or we decide, okay, we don't want to run that anymore. We run clear, and that'll stop it. You can also use it as a watchdog, so you can like run it. If then we hit the end of your particular loop, you can then clear it to say, hey, don't run, and then at the top run it again. And if you ever don't make it there, you know to run that other function, and that function can handle that error or that situation. Is running tells you that it's running, and these two here are error types. So delay too small and delay too large, and it kind of tells you what's the invalid delay that you gave it and what the minimum is actually supposed to be. And then delay too long is also the invalid value, and then also the maximum. I got rid of all the comments to make it easier to put onto a slide. But yeah, it's very simple. So if you were to write this yourself, the actual amount of code you need to write for this is actually not too intense. Any questions about the timer interface? Updated timer interface? Ooh, and I just remember one thing. The type here says continuous in one shot. One shot means that you run the function once after the time has elapsed and then you stop. Continuous means you run that once and then you run it again after that time elapsed again. So if it's like 500 milliseconds, you run it 500 and then another 500, another 500, another half a second, and you just keep doing it over and over again. I got rid of the type here because I felt that it was actually redundant with clear being here. So basically, if you want to be able to do clear, you can either have your callback call the clear for the timer object itself, or we can have an extension to timer that basically, after scheduling, it creates a wrapper function that takes the callback, runs the callback, and then runs clear afterwards. Basically, there's a way to do this that automates this for the user, and like it doesn't require them to actually do all this work themselves directly. And we can actually eliminate the other parameter here as well, so it's not necessary. So yeah, so now moving on to the big bread and butter, the thing that was really exciting for me and I think a lot of the people. Leaf. So before I go into the details about Leaf, because I've kind of been talking about it before, I'm going to talk about what the feats have been and what we've gotten across at this point. So Leaf, the limitations found. So I saw Leaf, thought it was, at first I thought it was kind of meh, because I don't think I read it really closely, almost at all. And I saw some other examples and stuff like that there, and I wasn't really happy with those ones. And eventually I went back to Leaf, and I started digging a little deeper. And I only learned about Leaf because someone on the C++ Slack, C++ language Slack, texted me saying, or messaged me saying, hey, you should really try out Leaf. I think it's a good system. I'm like, all right, I'll try it out. And it was actually pretty mind-blowing what it could do. And it had some ideas about it that I didn't really believe. I kind of brushed them like that. Doesn't seem to make any sense. Maybe they were just doing a weird way to calculate something, but the main thing here is that like I eventually fell in love with it, but then when I started to use it, I realized that there were some problems. Number one was that it used system error. System error has a little problem that I did not really like. System error actually is fine. No, never mind. System error is fine because system error is part of the exceptions class. Is what a string? No, it's not. What the heck? Am I wrong on this? Well, so it's not. Okay. When exception is associated with an error code. So I believe using system error internally ends up using std error code. Std error code has a problem because if I look at the message function here, it returns a string. Now that would be fine, except for the fact that error code, if I can find it, is it error category? One of these is virtual. So it looks like this one I think is virtual error category. There's a bit of a deepness to there's kind of some depth to this before you hit the end, but basically right here, this member function is virtual. You're supposed to implement this yourself. It's a virtual string message. Now, here's one thing about virtual is that if you make a function virtual, that function has to be linked into the code. And if you have a return type to that, whatever that return type is, also its whole facilities need to be linked into the code. If it was a normal function without like virtual in front of it, if you don't call it, it actually doesn't get added to the code. It gets removed. It gets garbage collected. If it's virtual, your code never knows when you may accidentally somehow indirectly call that particular function. So it needs to bring in all facilities to make that entire function work, including the return type, which means that we are forced to include std string into our code, even though we not want to pay for std string. So basically, std error code requires system error requires std error code, which requires std error category, which then requires std string, which then also requires malloc, and then you add in all of that into the code base for your error handling system. And although that might be the cost of operations, I was wondering if we can get rid of that. And I talked to the maintainer, the one who developed it, the one who created it, and we worked together in order to get rid of that. And this was causing considerable bloat in mostly dead code. If we're never using std string and we're not using malloc, then we are wasting space, or any other things for that matter. So that was one of the big issues I had with Leaf initially. The second one was that it required ThreadLocal storage. This is actually a brilliant way to handle this, and we'll see this in a little bit. But basically, ThreadLocal storage can be thought of like a global variable, but each thread has its own access to its own global variable. For example, arrow. So arrow is somewhat of like a global value that you get from including one of these things. See arrow. And basically, when you do things that are inappropriate or incorrect, like for example, if you do log of -1, you can then check the error node number, and it'll give like a domain macro type number. But basically, it's a global variable that you can check anytime you run a function. When you run those functions can update that particular error number. Now, there's a lot of problems with having something like this, because obviously, if you have, this is not thread safe. But Arano is made thread local, so it every single thread that gets created has its own version of Arano that these functions can basically access directly, and you check against it. The problem is if you use stock ARM GCC, and then maybe even with if I compile it differently, it'll work. I tried, didn't work out because I'm using a Mac. I'm not sure if that was the Mac problem though. But stock GCC for ARM basically uses emulated TLS, which is great, except it also turns it off when it's compiled. So you just get the same addresses to different. You get the same address basically back each time, and it just doesn't help you. It's no longer thread local. It's not like not every single thread points to the same object. It's not like each one has its own unique object to point to per thread. So that was not going to work. I was hoping it was just going to work and we didn't have to worry about anything, but it does not. So we had limitations found, but we also conquered these limitations. I worked with them the maintainer, to get rid of system error and look for any other problems that may have caused linkage of stitch string. They were able to get rid of all the stitch string implementations throughout their code. And just like, to give you a bit of a basis, at a very basic program I was using Leaf, wasn't really doing much of anything in Leaf, but the actual size, make sure I'm still online, cool. The actual size was about 8,500 bytes. Not a lot, because we have like half a megabyte, but still a considerable amount. We're able to bring that down to 1,712 bytes. Around about a 20% of the original value. The rest of that was just things that are going to be garbage or like unused code. Give you an idea of what that looked like. It looked like this. And I think, yeah. Very, very. It's a main. I'm going to go over what's all happening here in a little bit, but it's not too long. I even did a stack trace in this one. Did I do a stack trace in this one? I don't know if this is the one I used. It might be the one I used. No. Huh. I think I might have. Weird. Yeah. So this one actually has a stack trace in it. Cool. I didn't realize I did that with that example. But basically, we were able to reduce the cost of using Leaf, which was great. Another little thing that spent even longer. I think it spent around like 3 weeks. After let's say 3 weeks, a back and forth debate with the maintainer and myself, we came up with a solution for local thread safe storage, ThreadLocal Storage for any platform. And is actually direct. Yeah, we work together in order to get direct FreeRTOS support. So if I actually go to this little link here, if I have to go to the right spot, if you put in now boost leaf TLS FreeRTOS, it will automatically support FreeRTOS for you. You will need to set up the config num thread local storage pointers to the number of pointer types that you have in your system, which could be considerably large. You have to be kind of careful about how you define this. But it's something that you need to do. And this whole little section here explains in detail how exactly, if you don't have FreeRTOS, how to implement your own thread local storage for your particular application. So this is what we kind of worked on, is adding in this capability in the code, and also he added in all of this really nice documentation for us. So yeah. That's pretty much the limitations that we had to get through. And with all these things settled, there's literally no barrier for using Leaf. And that's why I'm really happy to, announce that we're using Leaf full on. There's no longer any back and forth. Now it's just going full hog Leaf as our error handling system for libembedded Hal. So now to stop beating around the bush, let's actually get a little deep into it. So with the next half an hour, which I know is a bit, but for the next little bit of time, I want to spend the time going over what Leaf is, how it works, what it looks like. I'm going to show you guys a couple of examples. These aren't real use cases and embedded. I think there's just these are helpers to kind of get an idea of what you can do with it. And then also some other really cool ideas that you can do with Leaf. So let's kind of go over here. So this is the documentation page. It's one whole page, and as you can tell by the scroll bar here, it is massive. But don't get too afraid. A lot of stuff at the bottom is basically, like from here on, is a whole bunch of API stuff. So it's all the API references, so you don't have to like go all that far. So a little less than half is something you may want to read. I think I've been here before, but basically, the same things that I talked about before. Single header, designed for efficiency, no dynamic memory allocation, which is freaking fantastic, even with heavy payloads. O of 1 transport, and I'm going to show what that kind of means in a bit. And then without exception handling, and support for multi-threaded programming, which now we can say is even more better supported. I think before it said like the library uses ThreadLocal Storage. I think soon we may have to reword this to say it uses ThreadLocal Storage, and if you need to disable it, like it says for some embedded systems, there's also a way to enable it for embedded systems if you're using RTOS, or something like that. So in order to basically pass along this information for error types, you need this thing called leaf result or boost leaf result. And you put whatever type you like in the middle. So it could be an int, float, whatever you were going to return anyway. Your code does some stuff, and if there's some error that's detected, you can basically pass or throw an error. Hold on one sec. You can return an error. I'm going to start using the word throw, even though it's not a throw. It's not an actual catch, throw from an exception. But it sounds a little better because I usually use the word throw in a lot of the contexts. And here we have this enumeration class, and we just threw error value 1. Threw that up. Now, you can also check to see if a particular result has an error. In this case, you can go results are result type T for R, some F, same thing that we had up here. And if, we basically do a Boolean check on it. If it's false, then there's an error. Return that error. You can bubble it up that way. Otherwise, you can just grab the error value this way. Okay? Any questions so far? Seem pretty easy. Wait to check, make sure I'm still online. Cool, I'm still online. Awesome. Okay. Yeah, so there's that. There's also this thing called boost leaf auto, which will basically assign v equal to whatever the output of f is, and if it does not have a value, it will bail out and return immediately at that point. I've actually replaced this with embed check, just because it's shorter, and also because rather than doing this auto v thing, you actually put the variable on the outside, because this is actually kind of confusing to look at and read. It doesn't look like normal code, but also you're forced to do this because not all C++ compilers support the having macros return values. So only Clang and GCC support that. We're only going to be supporting those two compilers at the moment. We may expand to other ones, but the other ones are kind of garbage and also not like that widely used, so it doesn't really matter. But that's a thing. So this kind of gets rid of the.
You can tell my work that.
So what?
Just wanted to say, if only you could tell my work that we use Visual Studios.
Oh yeah, no, like I'm pretty appalled that Microsoft had been using Boost Math without telling the guy that they had been using Boost Math for like 10 years, and then like apparently sometime recently they pinged him saying, "Hey yo, you have a bug with your math algorithm. Can you fix it?" And he's like, "What are you talking about?" Then he realized that, oh my god, you guys just copied my stuff. Yeah, so I've been hearing from the C++ community a lot that Microsoft does not the best job when it comes to building a compiler, and they almost broke std format really badly. That's a long story though. But yeah, so we don't support MVSC, Microsoft Visual Code for compiling C, so we don't actually have to worry about this particular thing here. Now here's the fun part: error handling. So this one's looks a little interesting. I want you, if you've ever used a try catch in a programming language, I want you to think about it like that. Think of this like our try. Think of these as our catch, where normally you put like a catch word here, and then you put like error 1 and whatever. Yeah, try to think about it like that. So in this case, we have this result R. We have this thing called try handle sum. There's a try handle sum and a try handle all. Try handle sum says like try to handle as many as you can, but if you can't handle everything, return back what the error was and let something else handle it. We try to handle as much as we possibly can in this context. This is useful in those cases where like in a normal exception handling situation, if there's no handler, there's no catch for your particular error, you would continue throwing up until you hit something that could catch you. And here we have like some F1 being called, save its value into V1. We have an F2, save it into V2, do some arithmetic on them or do some work on them, return that value. Hunky-dory, no problem. Now let's say at any point you're running F1 or F2, error 1, the enumeration was thrown. You could then check to see, hey, E is equal to error 1, handle that particular error, or handled something else. Hold on one sec. Yeah, so you basically have a handler here, and you can have multiple handlers. So in this case, this one's like a matcher where you can actually match the exact value, but you can have like a handler for matching a very specific value, or you can have a handler for everything else that's an error 1 type of enumeration. Here's one where you have an empty one. So like if you have to do handle all, you need to supply it with an empty handler. So if all other handlers fail, this is what happens when you can't match any other handler. And I'll show you some examples where this kind of happens. But yeah, you can keep kind of going and going and going. And things get even wonkier because you can even have different, obviously different types. Let's say F1 returns an error 1 and F2 ends up returning an error 2. Well, if F1 returns something, we might want to handle it differently. If we get error 2 sent out, we can handle that one. So it's very much like good old try-catch from JavaScript, or I would say better like Python or Java, where there is a specific type to each error, and you can catch on that particular type. And each one of these handlers is basically a lambda. They're just lambdas. That's all they are. Nothing too special. Now, everything here, is everyone kind of following this? I know I've been kind of scrolling through, but like, is everyone kind of following this so far? Or at least close enough?
Yeah.
Yeah.
Cool. So, moving on a little further. Here's things that get a little wonky. You can also throw multiple errors at once. So we have that little new error thing above. You can just throw error 1 and error 2. Nothing against that. Just throw them both. Here, that would invoke this particular handler. So you can have a handler for error 1, a handler for error 2, and then also have a handler for error 1 and error 2. So if you ever threw both of them at some point, this can actually match. Now, the order of operations is that the order in which you put the handlers in is the priority in which they are called. So if you have error 1, error 2, then error 1, then error 2, and this thing gets called, this will get called first. But if you had error 1 above, then error 1 will be called first because it saw error 1 first and to match with that. So I was going to take it back. That's actually not true. But there is a way to make that happen. But we're not going to go into that. I'll probably end up showing something that's an example of that later on. But that's the funky things that you can have more than just one error that you send out. And that becomes really powerful soon. Such as in this case, where, let's see if they have an example of this. Yes. So you can have an error of so there's another contract called onError. Basically says if there's ever an error, if you ever do like a new error, hold on a second again. If you ever have a new error, when that error occurs, every one of these little onError functions will then get called. That'll put in this case, E line, error line, current line, and we'll send that up. So when you actually, let's say you have a parse error of some sort, you can actually check it against what line it occurred on. So you can actually attach additional information on events where errors occur. And There's no limit to how many things you can attach to them either. And I actually abuse that, or really utilize that, in another example when I show how you can make stack traces with this. So now you can not only just have like, your typical like parse error, IO error, IO error by itself, but you can also have an associated error line, maybe even a file name, or even like, whatever else you want to do with it. Like you can put this information into your error handlers and make them basically more and more specific to very specific situations. Are you guys still following that?
Yeah.
Cool.
Yes, sir.
Cool. So, so now you can now get really specific with all this. If we kind of jump down a little further, here's a way that you can actually allow for cut what's the word I'm looking for? Optionals. So if you make this thing a pointer versus a solid type, what ends up happening is if you get an IO error, if you get an IO error, this handler will get run, with or without there being a line thing existing, a line object existing. So if this ever happens, you have to check to see if it exists. If it does not exist, then don't run this. But if it does exist, you can run this. I actually utilize that as well in one of the other examples. But yeah, it allows you to be able to turn off and on something, or like, not even like, have a function that returns this, but still be able to check to see if it did exist. So that's how you can get really specific with it, is by using pointers in this case. Exception handling, I'm going to skip over because we don't care. Then some other things we don't care about. But what I really want to show is this thing right here. I really like this. Oops, daisy. Did I click the wrong thing? Yes. Okay, cool. Okay, so the error communication model. This is for normal call stack, not using exceptions. Okay. When you make your handler, I want you to understand this. Oh, this is one little special thing that I really freaking love about this. So, when you return a new error, I'm trying to find a good line for it. When you do this new error, the thing that normally happens with most C++ libraries is that when you return a new error, you actually return those error values. A lot of times the way this would actually work is that they dynamically allocate some memory, give a pointer to the result type, and the result type would carry that up all the way to the top and then, do its work, and then it might be deallocated afterwards. It's not exactly bad, just means you have to use malloc. And, that could be, a little costly depending on how sharded the memory is, and if you're even allowed to use that for embedded. Another option is to make your result type nice and big so it can hold up most things, or you somehow put the particular types of errors you expect to come out of the result type into the actual type itself. So besides it being like result t, it would be result t, comma, error 1, error 2. But obviously that doesn't scale because it means you're stuck with error 1, error 2. You can't go any beyond that. This guy was like, nah, none of that noise. The moment you create all these handlers, it checks to see what parameters you're using and allocates those parameters on that same stack. And it keeps a reference to where those parameters are, so that when you run new error, it doesn't return any. All it does is create a result type with a flag set to 1. It's a union of whatever your type was, and some other error bit. Sorry, it's not a union. It's just whatever your type is, and then a bool, saying whether or not it's an error. The other thing's undefined at that point. When you do this, it writes directly to wherever that memory was at this particular location here. Not exactly this location, but that's kind of the idea. Is that if you look, if you look all the way down here to the model, when on error occurs, it writes it directly at where the handlers were, versus trying to return it up the stack and carry it up with it. Same with this one here. The moment you run E2 or you do new error E2, the value is written directly into the context of where the handlers were made. This is how it gets away from doing dynamic memory allocation. This is also the reason why it needs ThreadLocal Storage. I'll get into that in a sec. But basically, The moment you create a handler, you've now said that this thing is now handleable, and anytime we get an error for this particular error type, we will now write to that location. Creating that handler will set up a pointer, a global pointer for that particular type, saying, hey, for this particular type, if you ever throw this particular error, write to this location. And that's how we get O of 1 transport of errors. The moment you create an error is the moment that it's available at the catch point where you need to be. And all you have to do is make sure you bubble your way all the way up to the top to get to that point. And I think that's kind of the beauty of this whole thing. The problem is having a single global pointer to where the latest context is a problem. But if you use ThreadLocal Storage, each and every one of the threads has its own pointer to that local storage, and it can just point, it can go and throw that stuff up into its thread's version of that storage. So that all works out once you add let ThreadLocal Storage. Without that, yeah, it would be chaos. It would not work as expected. And yeah, that's pretty much what I wanted to go over when it came to Leaf. I'm going to show you guys more stuff. I'm going to show you some examples. I'm going to show you some stuff that I've done with Leaf in my experiments, in my testing, as well as like things I've kind of found here and there. You guys get a better idea about how Leaf is supposed to operate and how it's supposed to work. So 45, making decent time actually. Yeah, so let's look at this one. So we have a whole bunch of error structs. Notice that they're all empty. Well, because you don't need to hold on a sec. So notice how they're all empty because you don't need to put anything in them to make this thing work. They're just types. They're just separate types. As long as you throw different types, you'll be able to catch different types. So we have this function called square. It just squares a number. Now everything in here is kind of dumb. This doesn't make any sense. It's just way for me to control things. Yeah, so it just squares a number and returns back the value. I don't even use the value at this point. I just want to have something here. You can see that if the numbers between 100 and 200 or below 200, you basically have new error 1 type. If it's between 200 300, error 2, 300 400, error 3, and also error 4 because I can send multiple. Here we can see that I just simply run square. I didn't put anything else special in there. Just run square, return it. This is going to error out because I put 305, which is in between these numbers. And if you look down here, you'll see that error 3 is running, which happens when you have error 4 and error 3 together. I'm actually going to say error 3/4 type. And you'll see that pop up here once it does its thing. And we can see that this handler is running. And then return the value 200 that got put over here, and then we just printed that out. Oh, I don't know why I put not sum here because it doesn't make any sense. I'll have to rename this because that will never do. Because, yeah, that's not going to work. But yeah, so I'm removing that. That was a little check from before. If I change this thing over to 105, we shall get the error 1 detected. If I do, is there anyone that will go unknown? There isn't at the moment. Oh yeah, I can do this. I can remove this guy. If I remove error 4, this will no longer get run. And now the unknown error detected will come up. So we'll see that in a sec. Oh, I need to change it. Now what we shall see. There we go. Unknown error detected. So as you can kind of see, you can play around this play around with this yourself as well from the slides. You can see what things work and which things do not work. And if actually, I'm gonna try this out. If I put a pointer here, I think error 3 should work. Hey, there it is. So yeah, so like it becomes optional if you make it a pointer. And yeah, the code figures out all that information. Like, oh, you put in a pointer, so going to allocate the memory for it because we never know if it might get out. It might actually get put in. Allocated real memory on stack, and now we just pass the pointer to that over here. And if it was not allocated or was not set up, then we send in a null pointer. That's what happens. And yeah, that's pretty much what you end up doing. That's kind of how the different types of error handling kind of works here. And note that if I kind of scroll back real quick to here, I did put some members in here. I put those in there to kind of like for things for a user to print out, to be able to inspect, to log, because who knows, maybe the person wants to know that they messed up somehow and get better information, so like rapid prototype, or they want to log into the system saying, hey, some other system gave us a value that was incorrect. What happened there? So that's a thing, but you don't actually need to do this. Actually, case in point, I can show you an example that does not require this. I2C has a bus error. I'm going to zoom in a little bit. Zoom in, get rid of that. I2C has bus error and just not acknowledged. Is that it? I guess that is, yeah. And the thing is, they have no data inside of them. I was considering putting data in there, but we shall see. But maybe like the I2C that was not acknowledged, I'm saying the address that was not acknowledged, that could be useful. Although you kind of have it by the fact that you ran this thing, so you should already have the context of which one was not available. But maybe we can put that in there. But the thing is, you don't need to. You can basically just say, hey, you ran this particular function, address was not acknowledged. You have all the information you need at that point. You just need to know the type and the name of that type, really. That gives you all the semantics you need. So, going back over to this, you just have to throw types. There's no longer any data associated with this. There's no data in any of these. These are all a byte in size because the compiler has to give it some data, has to give it like some space. So it just gives it a byte. And that's pretty much it. So we can pass around semantically detailed errors without really sending much of any data around. But don't think that means that we can't send data around though. We can. Checking again. Okay, cool. Mic check. Cool. For example, let's look at this one over here. This one I love. I love this demo. So this thing kind of run a little bit. Cool. So if we look over here, ignore the warnings. So let me actually show you what's happening here. So if we go down to main, we have this try handle all. If you see in here, we have a for loop that basically runs the try handle a whole bunch of times, up to 10 times really. And I took this example from the Leaf example, so I don't usually code this way. I usually do this, but whatever. And we do a boost leaf check, and we're gonna run the stage 1 function with the number 5. The 5 in there is actually not important. It's really just to make sure that we can actually see the int as part of the function signature. So we give this thing 5. We say stage 1, tracer. I can go into that a little bit. Run the random algorithm, do a modulus 10, and if it's greater than failure percent, we do something. And the failure percent is 25%. Then if it did not fail, go to stage 2. If it did, create a new error. Oh, also side note, you can make blank errors, just blank. You can say there was an error and leave. That may not be super useful, but the reason why one of the error handlers still works is because we attached an error to it, and I'm going to go into that in a sec. But yeah, this stage 1 calls stage 2, 2 calls 3, 3 calls 4, 4 calls 5. If you notice there's some weirdness, there's like, I put a template in here just to make sure that came out over here in the name. 4 goes 5, and 5 almost never gets errored out or never gets called. Yeah. And here, what we can actually see is with every iteration, we can see if there's an error. So it says here, run number 0, error at stage 4. We have a stack trace here. So when error occurs, we have this thing called a universal error. Then we have a stack trace pointer. We have this thing called print trace. It checks to see if the stack trace is actually an actual value. I'll talk about why it wouldn't be a actual value in a sec. Okay. If it is, say error trace, get all the trace items and start iterating through. I feel like, where's the error at coming from? Check that actually. Error at. Oh, right. I just put an error there. Yeah, okay. So yeah, so we do run. It says an error. That's just inside the code itself. And the moment any one of these happens, we start getting the stack trace. Now, if we look over at Leaf, there's one thing that I didn't actually, I think I skipped over. On error. Oh, I didn't. So we have this thing called auto load is equal to leaf on error and this little current thing here. So if there's ever an error that occurs in this scope and gets returned up, this thing will be added to the list of errors for that particular event. There's another function called load, which kind of does this for you, but I don't use load, and I don't think there's any spots where we're using load, so it's not too important. But you may want to use it in the future. If I look over, there's a thing called stack trace setup. There's a lot of mumbo jumbo here. Basically, this little line here is a monitor tracer. I'm not sure what to call it, but basically this sets up stack trace. So basically returns back an on error object, which on error it'll associate a universal type with that error, as well as also run this lambda. You can also give it lambdas. You give it lambdas to do work in. So in this case, the lambda takes a file, a function, and a line, and a stack trace object. And I'll go into And from that stack trace object, it appends all the stack trace values into itself until eventually it's done. So at stage 5, if this thing errors out, it'll emit a universal error, and it'll run this lambda, which basically takes a stack trace object and then runs this. If you're wondering where the stack trace object is, the fact that you do on error with this particular lambda will allocate a stack trace for you. And it does it... where does it do that, actually? I think this is linked... Yeah, actually, I know how this works. So, how much do we have? 5 more minutes. More stuff we have to go through. Not much more. Cool. Just to wrap that part up. Basically, anytime you make you make a lambda in an on error object, it will look at the parameters and it will allocate those for you in a global context for that thread that you can then write into and alter and modify when that event happens. And let's say, here's the beautiful thing. Let's say I have this lambda here. Okay. And I decide to remove... I'm going to put some in here. I'm going to put in a printf, or a puts. I was called. We're going to see what happens on the right-hand side. And we should see a whole bunch of I was called coming up. Oh, come now. Oh, no, it's still compiling. I was called, and then we got all this information. I was called. Now, look what happens when I remove this. Oh, let's put a null pointer in there. Notice how all of the I was called went away. I have a handler here, but if I never put up I have this function here that was getting called before, but if my handlers never ever try to actually find them, Leaf will not actually call any of the handlers because it knows if you aren't, it's like this. If you aren't trying to catch something, I'm not going to put in the effort to write it. I will not run that function. The function has no destination. No one's ever going to catch it. Therefore, if no one's ever going to catch this error, then I will never actually throw the value that's there because the code will never be in a position where it can actually find it. And I think that is one of the beautiful and brilliant things about this, that like you can choose and opt into what type of functionality you want for your code. And the compiler can probably also eliminate a lot of that dead code as well when it realizes that this code doesn't go anywhere. I still need to do more testing on that side. That might be a lie, but I think that that's a really brilliant part of this whole thing, is that like No extra work is done if you aren't trying to read into it. And as we can see, we have a pretty nice stack trace. Now, this usually looks a lot nicer when you're not doing it on Godbolt because source is kind of lame. But it says, yeah, source 32 or 82, 95, 107, 107, location where this thing was created. Stuff like that happens. I'm still trying to get a way to figure out how to create errors when this occurs without using macros. Still looking into that. We'll see what happens. But that's pretty much stack tracing, as well as also using optional handler parameters. And now the thing is, since each error is something that a handler can opt into and plug into, it kind of becomes endless. Yeah, it ends up requiring you to have a pretty hefty number of types for your ThreadLocal storage. But I think that it's worth it. I think that it's worth it that you can basically, if you ever, let's say you're running on you're writing a CAN bus driver or an I2C driver, which is something I did recently for I2C. And I want to get a dump of all of the values inside the registers. You don't have to do anything special. You just do return, should probably put return here, boost, leaf, new error, CAN registers with an asterisk. That's it. Because it's a type, and you did asterisks here, meaning you're trying to do it by copy, it will copy the current registers from the MC use peripheral, throw it into its own local, its own global version of that, a thread local version of that particular object. It'll copy the contents. Okay. Sorry. When I say global, I'm dumb. No, it's not global. No. Sorry. I need to repeat something. The pointer to where the latest context is global, but this stack trace was allocated in this frame here. So when I removed it, this guy didn't have anywhere to write the data into, so it just opted to not write it. That's what happens, and that's a feature. So going back over to this, if you opted to have a CAN registers object in one of your handlers, if you do asterisk CAN registers, it'll read from all the registers from your I2C, and it will write it into that object so you can look at it later. Print out the contents if you like. How about going a little further? I talked a lot about how we're not going to really do logs in libembedded Hal because you shouldn't have any of your stuff read the log. But I got to realize that you can kind of get away with some log-like behavior by, doing something like this. I might just do shorten this down because I'm going to add a little something. I'm going to add bod, ebod type, so error bod. What I'm going to do is I'm going to say just too high. You know what it's a bod, right? So say too high, bod, and then another, and then bod max. So comma here, max, colon, boom, done. So what I just did is I kind of made a log of and I had this type that had that took a string of the first message, the baud rate that you're supposed to be expecting, the second message, and then the maximum baud rate. And we can have a printer for that. We can have a printf printer for that. We can have a format printer for that. We can have a OStream printer for that. It's pretty simple. So you could very easily kind of create these somewhat log-like messages with Leaf. Now, I'm pretty sure if the guy who made Leaf, the guy who made Leaf, he, him, yeah, that's his pronouns, sees this, me talking about this, he might think that's outside the range of what I expected this thing to be used for. But I think it gives us a really simple and also non-allocating way to give out somewhat error messages to a context that may want to see them. And if it opts to grab it, it can then grab it. And that, my friends, is Leaf. That's why I'm so excited. All of the actual APIs for libembedded Hal have been transitioned over to using Leaf. Let's see another good one Timer. Timer's already using Leaf everywhere. Leaf 100%. Leaf forever and always. So you'll see it all over the place in the code base. So yes, opening up discussion for everyone else. Any questions, comments, concerns about everything we talked about, whether it be reusable actions, timers, or Leaf itself? Cool. Seems like there are no questions or comments.
Yeah, I personally don't have any questions at the moment. I think this is just something I'm gonna have to absorb and understand over time as I do work with libembedded Hal.
Yeah, it'll take a little bit of time to get used to. It took me some time to kind of really understand the depth of what you could do with this thing. But I think the best way, and I don't know if you don't really use exceptions at work, right, Matt?
We do, but not actively.
Got it. Okay. Does any of your code that you ever touch ever like throw anything?
Yeah, we don't use try catch, but we do throw asserts.
Oh, asserts are different. Asserts are not exceptions. That's a different thing.
Gotcha. Then we don't at all.
Okay. Yeah, no. Does your program end when an assert gets hit?
Yeah, because it causes an exception.
Got it. Okay, that's a different sort of exception. Yeah, that's more of like a process exception. Okay, yeah. So that's using that's another paradigm for design. Rust actually does that. It's called panic. So if anything goes wrong, they say, "Oh, just panic, kill the program," which for some applications isn't acceptable. Like when you're writing software for a plane. But yeah, yeah. So for anyone else who, if anyone else who is used to try catch in like other languages, this I think lends itself really closely to that. Just looks a lot different. But I'd highly recommend for anyone who's still kind of like not sure to look at some of these examples in the Godbolt and play around with them to kind of get an idea of what's kind of happening, and also read the actual documentation. That's the documentation here. It took me a couple of tries looking through it to really kind of begin to appreciate what it could do and how powerful it was. Because yeah, having the ability to have just like any particular type be returned without and have all that be automated and have it also be small and code size was it's different. It hits different. It's very it's something I didn't expect I would see in a C++ without adding a language feature. So yeah. Any other comments?
I personally don't have any.
Okay. I'm actually going to show one little thing before we head out, which is the only place where we actually return a error. I'm still working on what the value should be here. But basically, we have a schedule function. It has a boost leaf result, callback, a delay. First thing we do is we stop the actual function, the actual schedule, the actual timer from going any further. So we stop the timer. We create a callable handle. Basically, this is a way to copy the callback in a way that the interrupt handler can handle. Hold on one sec. This allows us to take the callback and throw it and get it in a form that the interrupt service routine or interrupt vector table can handle. Once you've enabled that, the next step is to check the delay, make sure it's not below our minimum, and also check to make sure it's not above our maximum. If it's ever below our minimum, we just return a new error, delay too small, give them the invalids whatever they gave us. The minimum is what the minimum is supposed to be. Good. Don't know why it's saying it's an error, or I feel like something's wrong somewhere else in the code. And the same thing with our delay too large. And after that, If both of these are false, then we can basically reload the value, and we can start the timer. Although this is actually incorrect, I'm still working on the timing for this. This is not the correct thing. We need to do some math in order to figure out what the correct value is here. That's pretty much what you would do. If this was an I2C, you would do a return boost leaf new error I2C acknowledge blah blah blah. So throwing stuff is as simple as kind of returning a new error, and catching it's the part that's a little more complicated. I think for almost anyone who's writing drivers, you will almost never, and almost should, as a policy, do not try to handle error inside your driver unless you know exactly how to handle this error. For example, if you have like some chip that says try to read this byte, if this particular flag is set to 1 or something like that, or if the device like says non-acknowledge, try 2 more times, and it should work. If it doesn't work after that, then there actually is an error. If that's the case, then you should handle it. You should actually handle the error when it occurs, try a couple more times, and then throw a bigger error if that's the case. But otherwise, just throw the error. And that goes for normal exceptions as well. Because you don't know the context in which the user or developer may want to actually handle it. They may want to handle on their side. Give them the capability to handle on their side. But yeah, I think that was pretty much all the things I wanted to talk about today. Yeah, that's pretty much it. I'm going to stop the recording right now, and then we can, if anyone has any questions,